applications. The name of the session is Advanced Services and Applications, and the presentations are, well, each is quite different. The first one is Pekal. She will be talking about the technologies for building content delivery networks. Content delivery networks is quite a trend, I think, recently. It's very interesting and important, in my view, in that it changes the way the internet works with application level routing and that kind of concepts. Pei has received her PhD from Princeton University, and after that she spent a couple of years with academia, and recently she moved to Cisco Systems, where she is the technical head of content networking unit, I guess. So she's the best person to tell us what is the current state and future of content delivery technology. She's also member of the steering committee of Worldwide Web Caching Workshop Conference, and I have to say that she's been very brave. Yesterday, in getting past the Turkish border to join us today, but she made it. Okay, the floor is yours.
Thank you. I had quite a bit of adventure of coming to this country, and that's what he's alluding to. Okay, can everybody hear me? Yes. All right. I will talk about technologies for building content delivery networks. Due to time constraint, this talk is more of a overview talk rather than being able to get into the details of each technology component. So hope that's okay with everybody. And if you have questions after talk, you're welcome to come to me and we can talk more. Now, what is content delivery networks? Basically, content delivery networks is essentially a collection of content delivery devices that is centrally managed and interconnected, and they coordinate to deliver content to the end user. And it has become popular and useful because it solves two problems. One is the problem of bandwidth. If you have a large video or a lot of web content you'd like to deliver to 10 million internet users, obviously if you only have a central website, you need a very fat pipe from your central website. And content delivery network, by distributing the content around the internet, is a very nice way of solving the bandwidth problem. The other issue it solves is the server throughput. As we all know, individual servers and computers have limited throughput, so by having a bunch of servers serving the content for you, that's very useful. Now, if you look at the simple definition, it actually didn't say what the contents are and who the end users are. And in fact, there are a lot of content delivery networks. And the word itself is confusing because many people use it in different ways. But roughly based on the category, we can see that in terms of content, there are roughly both static web pages, and that gets distributed. And the best company, as an example of doing that, is Akamai Technology and the Digital Island. And then there are contents that are video for distance learning, for training, and for the e-learning markets, content delivery networks, most of their customers is in fact enterprise environments. The other issue is that there are, in terms of where the nodes are placed, sometimes the nodes are placed around the internet, and essentially you build an overlay network around the internet to deliver contents. But sometimes the network can be as simple as just part of the enterprise premise network, and this is mostly used when enterprise themselves build a content delivery network to deliver video content for e-learning. And finally, in terms of the users that the network is built to service, could either be all the internet users or could be just employees in enterprise. So as you can see, the content networking really could mean a range of different things, but they all share a common set of underlying technology, even though because of the different environment and different users, it has an impact on the actual algorithms used in the underlying technology. And I will describe some of that in the talk. Now, what are the technology components in building a content delivery network? Roughly, there are four. One is obviously distribution. Once you have a set of nodes out there in the network, how do you place the content out there? And the other is request routing. That is also people sometimes allude to application level routing. And this is how do you steer a user to a node that's close to the user? Because we'd like to, in a content delivery network, to make sure that the content arrive at the users either in low latency or have certain quality of service guarantees. So request routing is quite important in picking which delivery device should serve which customer. And finally, of the edge node themselves, they are content delivery node. So these are the ones that actually speak the layer 7 protocols and actually serve the content to the users. And in the content delivery, in addition to the protocol processing, it also enacts access control and also making sure of QoS guarantees. And finally is resource accounting. How do you build the services, or how do you just keep track of how much content has been served to what clients? I wouldn't be able to spend much time on resource accounting in this talk. Okay, now content distribution. As we said, the goal is to place the objects onto the delivery devices. Now, this isn't so important or isn't so critical for static web pages or generally small objects, because for small objects, it's almost any method will do. You can either try to FTP a tar file of all the objects over to the nodes, or you can just simply do demand pooling. When the request arrives at a node, you pull the objects. But it becomes critical for large objects, especially with video presentations, or think of a 30-minute presentation of some training video. So for these type of larger objects, you usually pre-position them. And it's the pre-position technology that is interesting in terms from a research point of view. Finally, on dynamic pages, usually for dynamic content delivery, you need some kind of prior setup or some more advanced protocols set up between the two. Microsoft.NET has certain aspects of it, but in this talk, unfortunately, I wouldn't be able to get into more details of it. Suffice to say that this is still an area of active research. So what are the distribution mechanisms? Now, for HTTP requests themselves, for simple static pages, the distribution can be purely on demand. The delivery node, when the request hits it, gets the web page and then cache it. And standard HTTP reverse proxy or FTP of tar files or whatever. And in fact, some content delivery device vendors, their delivery mechanism is simply the FTP of tar files. Now at Cisco, one of our main focuses is on large streaming files. And for these, they need to be pre-positioned, usually at nighttime when there's not much use in the network. And also we pre-position them in a rate-limited fashion. So you can imagine all the delivery nodes on your network, all the delivery nodes in this network, in fact, build some kind of tree structure. You can think of this as application-level multicast, except every node to node is quite reliable. Anyhow, you build this in a tree structure, and the contents are delivered from top level to the second level. Then the second level nodes then position the content onto the third level. There are also recently a lot of proposals on using multicast, and this is obviously very reasonable since the contents you're wishing to pre-position are the same contents. Now here, there's also a couple of examples. There are application-level multicast, and one good example of this is infamous fast-forward network technology. And then there are unreliable multicast with file-level error corrections. So these are techniques where you take the video file and then you use mathematical transformation to transform this file into a form that essentially you can, even if you lose M out of N packets, as long as you get the n-m packet, you can still recover the whole content error-free. So this is typically called forward error correction or file level error correction. And there are companies these days that essentially what they do is they do these transformations, and then they send the files using unreliable IP multicast. And one example of this is digital fountain. You can think of simpler to this ones like multicast FTP, but that is not as sophisticated as digital fountain. And also in terms of unreliable multicast, there are also vendors that build content delivery networks with that. These are examples like real networks, broadcast networks. In these cases, the media itself can deal with lossy transmission themselves. Now, with content distribution, obviously you talk about content consistency as well. Here, in addition to the traditional mechanisms where you set up expiration time or time to live times, recently in IETF there's a group effort that's trying to build an invalidation protocol across the internet. And specifically, the idea is that any delivery node in any content delivery network is capable of receiving invalidations or be notified of resource changes. One particular protocol that's being worked on right now is Web Cache Invalidation Protocol, or the WCIP. The idea here is that for scalability reasons, the content objects themselves are organized into channels. And we expect that for the content that has a lot of receivers or had a lot of interest, they tend to be more correlated, and we wouldn't need many, many channels. And then that nodes that wish to receive invalidations can subscribe to the channel. And as channel broadcast invalidations or the updates of the contents, other nodes will be able to receive it. And for those of you who are interested, I encourage you to look into the IETF group. I believe the acronym is WEBI. And that group has a web page on WCIP, or just go to Google and search for WCIP, and you can have more details on that. That's about as much time I have on content distribution, and I will switch and talk more about content request routing now. So the idea of request routing is that you'd like to steer the user to a node that is close to you. Now here, when we mean close, is that we mean a node that can give reasonable service to this client. The node doesn't have to be closest, because closest in the networking sense is often hard to measure and hard to guarantee. In terms of methods, there are roughly three categories of methods: DNS selection, HTTP redirection, and transparent interception. Now, before I get into the details, let's review how a request actually arrives at a particular server. Now, in this example, let's say that I have a request for www.xyd.com/index.html. This is the URL I type in my browser. Now, how does my PC actually go to the server and fetch the content? It roughly goes through the following process. The first thing my PC does is, what's the IP address of this web server? And it asks, is DNS name resolution server of this particular question. Now, either the server has the answer cached, or in the case that it isn't cached, it has to first find out what is the name server of xyd.com, because only from the name server you can get the IP address of the actual machine. So probably go to a root level name server and say, what is the primary name server of xyd.com? Root level name server, and then send an NS record back and point it to the name server at xyd.com. Then my DNS server will then talk to xyd.com's primary name server and ask the question, what's the IP address of www.xyd.com? And then the name server there will send back an A record, in this case, say 1.2.3.4. And once my name server receives this answer, my name server will put it in the cache and also send a reply back to the PC. The PC then sends a HTTP request to 1.2.3.4, and this HTTP request probably goes through a router in my ISP, and before it hits the actual server machine, it actually also goes through a switch, usually an intelligent layer 7 switch. So as you can see here, there are in fact many places you can actually intercept this request and try to steer it. So the detail of the DNS selection methods for request routing, the idea is that you have a special device that is the name server of xyd.com. And then this name server, when it sees the request coming in asking what's the IP address of the web server, it will be able to, based on where the request come from, give different answers. So that's the very basic idea. Now you might ask, well, how do you become xyd.com's name server? There are typically two methods. You either, for the objects that you are trying to be serviced by the content delivery network, you rewrite the URLs. And that's essentially what some of the service vendors do, like Atomai. So they actually rewrite all the objects so that the objects are objects in Atomai.com's DNS domain. Or in the case of an enterprise, you can take all the videos and put them in a domain cdn.xyd.com. Then you purchase a request router from the vendor, and the request router itself acts as a name server of cdn.xyd.com. One special problem with this set of method is that the accuracy, if you look at the previous slide, the accuracy of the selection is the position of the DNS server of the client PC. Now, this isn't much of a problem if you are delivering content to the internet, the general internet, because typically a particular client's DNS server is close to that client. But this wouldn't work very well if your environment is some kind of cable network or in an enterprise. For example, in a cable network, there could be thousands of clients, but their DNS server is the one that had npop. So for those type of environments, you would need a second method, which is HTTP redirection. Now, in HTTP redirection, the basic idea is that when the request hits the web server simply says, oh, go somewhere else. That somewhere else is a node closer to the client to fetch the content. So what happens is that when the HTTP request hits the web server sends a 302 redirect and tell it to go somewhere else. This wouldn't be very efficient for general static web pages because you essentially have to go through two request round trips to get it. But it actually works very well for multimedia objects because the way that the multimedia objects are organized on the internet these days is that the audio track and the video track and the associated slides are actually all organized in a particular index file. For example, in real media, that's the .sml file, and in the Microsoft, it's .asx file. And before the playing of the video or audio, the client actually go fetch this index file first. So that's the place where you can do this redirection and get them closer, redirect to a node closer to the client. So the accuracy is at the individual client level and makes it more suitable for enterprise or cable network. The last method, transparent interception, is playing tricks at the routers and the switches. And most particularly what is used is the tricks played at the switches. And this is used in a case where, suppose you have a data center in North America and in Europe and in Asia, and you'd like to be able to redirect the request so that the clients in Asia get serviced from a server data center in Asia. And what you can do here is actually play tricks with the layer 7 switch, where when the request hits the layer 7 switch, the layer 7 switch intercepts it, and then essentially hand the request off to somewhere else. You can think of it as a triangular TCP, where the streams come one way, hit one point, that one redirects somewhere else, and then the return stream come from another place. That's the mechanisms. What about the algorithms? Now, the algorithm for request routing these days is still actually very much a research topic because obviously trying to figure out what is the closeness means in a network is a research topic. Now, there are typically two sets of algorithms. One is map-based and one is recent-based. Map-based is very simple. You essentially keep a set of maps of AS domains on the internet, and you try to direct client to a node with the least number of hop counts to that client. And a more interesting one is actually arrays-based. And a good example of this is the boomerang algorithm that people at Cisco has developed. In this case, what happens is that the name server themselves actually, once they receive the request from the client, forward this request over to all the delivery nodes. And then the delivery nodes themselves all form an A record with their own IP address as the web server IP address and send it all back to the client. And whichever one gets there first wins, because the client-side software usually just take the first answer and ignore the rest. So this way, you let them naturally select which node is closer to it. Obviously, at this point, you would say, oh, this wouldn't scale at all. You have a large number of nodes. You would be issuing a lot of these A record messages. What you can actually do is each time only select a subset of a node to participate in the race. And then the next time, you pick a different subset, but including the previous subset's winner in it, and try to refine in that process. And for those of you who are interested in detail, the paper is actually published at the web caching workshop this year, and the proceedings will be online soon. Now, there has been interactions between the content routing and request routing, content distribution and request routing, in the sense that you should never route a request to a node that actually doesn't have the content. So typically, this is particularly important for large streaming files, because by the time the request gets there and you try to get a file, it is too late. So what usually happens is that the content delivery node themselves have communications with the router and notify router of the replication status of the node. And that's about much time I have with request routing. And I guess I have 5 minutes. Okay, let me just quickly zoom through the delivery aspect and accounting aspect. Now, content delivery node is mostly built by web caches or splitters, and it essentially have to support all the delivery protocols, HTTP and streaming protocols from both Microsoft and Real Network and open standard streaming. The content access control is an aspect of the delivery node. Particularly here, typically you associate objects of publication date and expiration date, and it has to be have access control based on user group. And I heard that there's a new session on access control later on, and as you can see that content delivery networks will be able to use whatever access control there is. One thing about the quality of service here, the quality of service in content delivery actually have two aspects, the server side and network side. In the server side, you have to make sure that a node that sign up to deliver a particular stream have enough throughput to do that. And this typically requires some communication between the delivery node and the request routing. And this is, in fact, a research area that people are still working on. In terms of network QoS, you'd like this to be set up so that they interoperate with the routers using diff service or whatever mechanisms there is. Resource accounting these days are pretty much still at the stage of mining log files. And although there are some proposals where the switch themselves actually set up customized MIPS of recording how much throughput has been done on a particular domain and be able to send those MIPS in real time to outside resources. Now, in terms of Cisco CDN product, Cisco right now has 4 lines product that complements the CDN solution here. One is the content distribution manager. This is the one that handles all the content distribution, and it supports both rate-limited replication and multicast using error correction code. And content router is the request router component of it. It currently uses the boomerang algorithm, and it also has the map-based algorithm in there as well. Content engine is the part that I actually work on very actively, and we support all protocols and have high throughput. Finally, the content switch is the one that offers fault tolerance of content delivery devices and also have support the distributed data center. So in summary, I told you very quickly major components of technology used to deliver a CDN, a distribution, routing, delivery, and accounting. And remember that the CDN system requires all 4 components to work in concert with each other. There's some works in IETF that's trying to standardize part of the interaction, but there are still aspects people don't understand very well yet. and Cisco is the only vendor that provides the full solution. That's it.
Okay, thank you very much, Pei.
Thank you.
We can have some questions, probably one or two questions. I don't see any questions.
I probably confused everybody.
Just wait for the mic.
Okay, my question is about the content distribution. One of the methods of doing distribution you mentioned was multicasting.
Yes.
How do you see multicasting in the future? Is it going to grow, or is it something that's been currently tried but it's not made suitable?
I think it's going to grow. There has been a lot of interest in multicasting from my interaction with customers. And enterprise would like to use multicasting for e-learning and broadcast of company meetings, and there are a lot of interest in that. One particular issue that we run into there is that there are a lot of ISPs that are kind of anti-multicast and is having problems. And that's in fact one of the things we hear a lot of complaint about from our enterprise customer. So my feeling is that it's going to grow.
Okay, thanks.
Any more questions? If no, then thank you again.
Okay.
And the second presentation is the title is Telemedicine in the New Millennium, Just Participating or Faster, Higher and Stronger. And Heinz Weber of University of Erlangen will give us a survey of what is currently happening in telemedicine, what is already possible there, and what are the possible obstacles, how to overcome them. Dr. Weber specializes in vascular surgery, right? But he is also very active in coordinating numerous telemedicine projects in Germany, so he's also the perfect speaker for the topic.
Thank you very much for this nice introduction, dear ladies and gentlemen. I really appreciate the opportunity to present you an update on telemedicine, what was up during the last time and what are our future aspects. As you already mentioned, there's a subtitle, and it's the question for us from the medical field, is it the Olympic spirit, just participating, or do we really have to compete and it's faster, higher and stronger? Maybe my talk was accepted because Manfred Bogen's question last year was, what do you do with all the blood in your transmissions of data? Well, we found the answer. We evaluated a special research project where we combine CT scans, MR scans, as well as two live video cameras in endoscopic surgery, send them to a computer, and this computer calculates the wrong color, such as blood, away. In fact, we don't need it as much for blood as a wrong color. We need it for calculating reflections away, so we can see a clear picture again. Let me give you an overview on some applications that we had in the past, or that we are focusing, or that are happening right now. There is some robotic surgery, some simulator surgery, computer-assisted surgery by replacing doctors through computers. We have 3 different ways of teleconsulting, having a second opinion, which every patient would like to have, either immediately, which means telepresence, or a telesupport, where you have some time left until you get an answer, or a frequently asked question board. For educational purposes, it's important that you have an interactive opportunity for the audience to answer or to ask the surgeon. We create medical networks and telematic platforms. The general infrastructure I would like to leave apart, because electronic prescription is not that important for network people. We have been setting up quality control centers, multi-center studies, which makes research in medical fields much easier. Telesurgery is always a question. You can accept telediagnosis, and I'm very doubted on teletherapy due to the fact that nobody who evaluates networks would really rely on his own networks and be my first patient in performing telesurgery. Please let me know if you would like to be the first patient. We have a simulator. Simulators are for research and for educational purposes. You have the surgeon standing there and seeing a virtual picture. We have robotics roboter arms holding the camera like you see in this case, where you have a performing surgeon performing an endoscopic thoracic sympathectomy, just assisted by the robotic surgeon, and he's following by word. You have to claim him, and he's positioning the camera. You can do that as well from a remote location, but there's no need for that because you have the computer in the operation room. If you think of a second opinion, you need networks everywhere available, and the only field that is available everywhere nowadays is ISDN, maybe ADSL coming up, which makes costs relatively low, and you can transmit the still standing data in endoscopy, sonography, and pathology very good, but it's very critical if you have higher data volumes. We even perform ISDN transmission from our operation room. Jeff Milsom from Mount Sinai Hospital used to transmit his operation via 3-channel ISDN, 6-channel bundled from Mount Sinai to our hospital. We have right in the back a surgeon from Italy, and there was only one ISDN line available from Italy, from northern part of Italy. So thanks to his stoic quietness, we saw here a brilliant, sharp picture from him. If we talk about networks, we have to think about the connectivity. We had the lucky situation that we were supported by the DFN, the German Research Network, and had the chance to evaluate the gigabit testbed south. So we had a high bandwidth available between Erlangen and Munich and up to Berlin. But we started with modem connections. You all know much better than I do about the bandwidth of ATM services, satellite connections, and now giga networks with video over IP possible. If you have a look at this instrument, this is the instrument the surgeon performs an endoscopy with. You see the hand of the surgeon, and you can twist it forward and backward, turn it left and back. Even if you rotate the whole instrument, this makes a difference for the patient. You can suction, you can blow air into the patient, and now you have to transfer all this data reliable to a network. If you have a solution for this problem, then teleendoscopy might be possible. On the other hand, we have many networking facilities available, so we use them for managing our connectivity, like in the eastern part of Bavaria, where you could reduce the alarm time for medical people necessary to treat patients. You have an ambulance doctor out, they send the data via GSM, and they are transferred via ISDN to an emergency organization, and so the hospital knows much more about the patient that is coming up, and even acute hospitals can transfer the data to the university hospital. But think of the input machines. Would you trust the doctor looking like the guy on the right-hand side up there? Or touchpads, transferable, portable touchpads? They need to be much smaller, and we have to rely on the data as they need to be transmitted. Let me focus on education a little. Education in the past, you had an auditorium watching what the guy in front of you was talking, maybe even having an operation being performed there about 20, 40 years ago. But nowadays we have the chance to transfer these operations live to the internet. Thumbnail pictures, they even grew better, like we see here at the workshop where we do the streaming. We can produce these web streamings, what we did in the past as well. Maybe the future looks like that. Every surgeon having his own satellite, I think that's way too expensive. Don't forget about the manpower. As doctors' fees are not yet guaranteed, we don't get paid anything for setting up such a telemedicine network, nor for having people that help us with that. You see the operation room camera with a camera in front of in the middle of the light. So you save one person up there because the operating surgeon tries to focus his light best for the operation. So you have a brilliant picture. Giving a microphone to the operation makes it much easier to work with the surgeons because they are much more friendly if they have a microphone than if they don't have one. So that's why we have 12 operation rooms equipped with microphones, apart from we just switch 2 of them on. If you have the input facility there, you can either input the picture from the ceiling camera. You can input an endoscopic picture, you can input a laparoscopic picture, as well as sonographic pictures, ultrasound pictures, whatever you need. You need the manpower for presenting those pictures. You need one in the direction room for switching off between the operations. See Professor Feussner here, who is telepresent as guaranteeing the quality of service in surgical needs. He watches the operation, and if you think he watches the operation shown on the right upside from the screen, you have to think of the latency. So if he talks about to the surgeon, the time, there must be no time gap between his answer or his comment. Of course, you can transmit those data as well to a big auditorium, and students will profit from that. Last year in October, we had the World Congress of High Tech in Medicine coming up, where we transmitted over 90 live operations from all over the world. 70 hospitals were connected. Most of them, unfortunately, connected via ISDN. Due to some contacts at last year's Terrainer conference, we tried to get some connected via higher bandwidths, but there were several difficulties in the local networks to get them connected to us. So we only had 155 megabit STM1 connection and one 2 megabit E1 connection. And imagine the fact that the whole auditorium saw the brilliance of the pictures. So we had the College of Surgeons, their yearly conference 2 weeks ago, and they all said, no, we don't want to have ISDN connections any longer. We just want to have the video over ATM connections. So we had 4 live operations with a video over ATM connection. Everybody was impressed by the brilliant quality. They were impressed by the live interaction that was possible there. You see them on the right-hand picture down there. It's very interesting for surgeons if you have 2 patients with the same disease and 2 surgeons treating them with different methods. So you can compare the methods and can ask, why are you doing this? Why are you doing that? Next year's surgical conference will have the main topic, digital revolution, and maybe if you have any ideas how to implement new techniques, you just let us know. We even informed patients at CeBIT 1999, 2000. There were many people watching the live transmission of the operations and were interested in either what we were doing there and either in the capacity of those platforms. Even we medical people, I know we are a little late, start surfing the internet. We did that in creating some web streaming, performing some live operations. Of course, live operations for the internet only for educational purposes. Due to the delay, we have a delay of about 18 seconds until the picture is in the web. And if you imagine the interactivity necessary, which we did in the beginning with email to the operating surgeon or exploring a chatbot, then you know what is our problem. If you have, as I just mentioned, this web streaming, we did that in December with a heart operation. There were 10,000 live spectators, and since that time, by yesterday, 500,000 spectators. We had a supporting chat, but the main important question in the chat was whether Professor Weyand, as you see him on the right-hand side, was married. So there were not only interested patients, but as well just people looking at it for fun, and that's not what we need the technique for. You see the equipment with the external camera on the left-hand side, and as I mentioned, the manpower. Do we treat the patient with a mouse click? I don't think so. I think computer-based patient records are good for any patient. Of course, you have to take care of the safety of the data security. But it's much easier to click on a computer and have an access to the CT scan rather than running around about half an hour in the whole house and asking, where is this computer scan? Of course, we can do documentation by having networks available that gives us the chance to documentate either videos or pictures and to add them to a computer-based patient record. If you have a look at these angiographies, you know there is a stricture somewhere you might want to like to place a stent. What you need to know is how do these branches go off from this main stem from the artery, as you see the aortic arc here. And as you see on the left-hand side, if you rotate it, you get pretty good an idea on how long this stent may be. So we create a multimedia computer-based patient record where you can put in all those data, and therefore we need very good networks and we need ideas on how to create that. Do we create a patient that is from glass so everybody can have a look at it? Probably not. I already mentioned the digital signature is of course one thing that we try to use for getting access to the patient data. We need one for the doctor and one for the patient, and only if those two fit together, then you have the chance to access the patient's data. We have many telemedicine platforms available worldwide. But who controls the content of these platforms? There's a really flood of information, and I think the Society of the Doctors has to check that this content is okay and this is real good content. So we have to create 3 layers: a public layer with the information, a communication layer in those platforms where the people who have access can transmit their data, and last but not least, the computer-based patient record. Another focus on new technology. We find cable salad is a horrible thing, and I hope in the future we don't need the rectoscope to protect this cable from breaking. This is telemedicine in real situations. I hope infrared and Bluetooth might bring us solutions for this cables you see hanging out there on the right-hand side. I mentioned the latency. Here you see a picture. We measured the latency with our video over ATM codec. And to understand it, the problem in the latency is not the ATM line. The problem is the encoding-decoding process. We have a decoding, encoding time from 200 milliseconds, which is, well, pretty tolerable. But let us have a look at the picture quality. If you have the source quality picture, it's a multiband with different bandwidths. Then you have an ISDN codec who just drops half the frequencies. Then you have an E1 connection. Nobody could describe what happens over there. And see the ATM codec. Here you see the slightly compressed frequency on 6.5 megahertz, which is not really too bad. The sharpness, if you compare the source to the encoded picture, it's a little blurredness, but it's a symmetric error. So if you focus on, please take care, and if somebody would like to fall to the ground, rather turn around now. It's an aneurysm of the splenic artery, and you have to transmit those data, and on the right-hand side it's the encoded picture, and it's fairly good because we can still get an idea about the branches of this artery, and we can explain him which branches to cut and which to keep. What about the future? We need a systematic documentation. We want to have a mobile use. Even we are very interested in getting wireless LANs, even accessible in the operation rooms. We ourselves have to organize the transmission of our data, and we have to connect horizontal and vertical the existing networks. Means we need to connect to our clinical information systems. What I mentioned before is we should try to connect different countries. We are talking about a worldwide internet, and it figures out that we have several local networks available, but connecting them might be a little difficult. Of course, we like to use faster networks. We are looking forward to video over IP. Imagine always our problem with the latency is one surgeon telling the other what to do. You cut until I say stop. If you'd like to be the patient and the latency is 8 seconds, then thank you very much. And our big problem, who pays for the service? I mentioned nobody until now paid for the service, so we focus on our sponsors and on people who are interested in that. Do we want to create teleconferences? Of course, it saves time and costs. But if I see that even you, the networking people who used to figure in teleconferences, create such conferences in such nice places, I think we from the medical field don't need to do that. And apart from teleconferences, the social contacts beside those conferences are very important. Let me thank all my co-workers in the end. First of all, Professor Hohenberger, the director of our surgical hospital, Peter Holleczek from the local computing center, Professor Feussner from the Munich University Surgical Hospital, my co-workers Susanne Götz, Tatjana Hetz, Sabine Jordan, Andreas Angemeyer and Jochen Adam, who are working in Erlangen right now, performing a web symposium for our heart surgeons. And last but not least, the DFN, the German Research Network, who accelerated our efforts in creating telemedicine a lot. Thank you very much for the attention.
Thank you very much for this interesting presentation. Do you have any questions to this? Very There's a question over there.
Thank you. What I really like to know is how do you deal with all the radio signals in the operating rooms? I mean, usually we are not allowed to wear cellular phones in hospitals.
I don't have any radio phones in the operating room. I have a cable from the camera running down to the interface where you can input all the signals. You have lots of cables. You have the only radio thing you have is the microphone from the surgeon, and this doesn't interact with all the other equipment there. And then I have cables running to the directions, so this is no problem at all. Unfortunately, we can't use the wireless LAN. That's what I mentioned before, because this would interact.
Okay, and Thomas here.
My question is about the video quality. You showed us the picture via ISDN, E1 and ATM. Do you know what the codecs are? I mean, as far as I know, the ATM codec is a motion JPEG codec. Do you know about the other ones?
Yes, we tried out several codecs. We use a codec from Tektronix, which is an MPEG-2 422 codec. We tried out a 420, a main profile at main level, and an MPEG-1 codec. We tried out one from Newbridge, one from Latenn, one from KNet, and we had several problems with those codecs. The latency was, the minimum latency we could reach with the main profile at main level was 95 milliseconds. But due to the fact that MPEG-2 coded 422 pictures are much better from the quality, if you need to know about the details, then people preferred accepting the longer latency in this codex rather than having a much unsharper picture.
Any more questions? There's a question at the end there.
The examples you showed us were all about live operations. Do you have everything available on demand afterwards and indexed every operation?
Yes, we have it on demand. If you connect to our website, chirurgie-erlangen.de, there you can get access to those operations. There are two main domains in Germany, which is Blick in den OP, Klick-in-den-OP.de. They are listed there on demand as well, but the main listing from our telemedicine activities will be on chirurgie-erlangen.de. It's just updated, so as soon as I'm back, you will have the videos on demand on Monday back again.
Anyone else? If no, then thank you very much again. And the next presentation, this is different to the previous two ones in that it concerns a specific project. Thomas Schmidt will talk about a prototype time-driven modular multimedia presentation system that he has developed with his colleagues. Thomas Schmidt is head of the Computer Center of Fachhochschule für Technik und Wirtschaft in Berlin. After completing his PhD, right? After completing his PhD in mathematical physics, he is for the last several years involved in many projects in computer science there. And the title of the presentation is Media Objects in Time, Multimedia Streaming System. Thomas.
Yeah, thank you for the nice introduction, and thank you for giving me the opportunity to speak here. I want to introduce to you today an ongoing project in the area of multimedia teleteaching, and it rather deals with multimedia applications or how to create multimedia applications than with actual content delivery networks or so. The project has two focuses. One is the point media objects, and the other one is time, and I'll try to explain this to you. First, I'd like to give you some introductory ideas, and then I would like to convince you that modeling media objects or modeling in the multimedia way is something of interest and something important. And as a third, I want to present to you a multimedia environment and information or application modeling environment, which is sort of, if you want so, a multimedia middleware. And as a specific application, I will show to you the media objects and time system, which deals with synchronous media streams, which has filled the general model in a specific way, and it also includes a video codec, a wavelet web video. Well, if we believe that network multimedia has the potential to revolutionize teleteaching, then we have to do something more than just donate web pages to people or PowerPoint. And the picture we have in mind is that our teachers are able, with the multimedia equipment and the lecture halls, are able to supplement their lectures, their courses, by just picking media objects, media entities to illustrate what they have to say. And on the other hand, we'd like to donate to students telelearning applications, which means more than just having some web pages. And this brings me to the statement that to come up with more complex and interactive applications, which we have an urgent demand for, we need to do something. We need to provide an infrastructure, a high-level infrastructure for teachers to come up with multimedia applications. So, what will be the specific goals we have? Well, we want to present or provide an environment where it is easy to implement applications, specific educational applications on. And first of all, we need to be free in the information layer. We need to be free in the definition of annotations, like objects, media objects have more than names and authors. They have subjects. They have additional informations. They may be ordered in keywords. They may be structured in a sense, and they may have meta informations like from a didactical or from a technical point of view. Well, we also want to provide a general media handling, of course, including streaming, which can be easily employed for nonlinear structures. The nonlinearity is, of course, something new to the teaching, but is brought with the web and hyperlink stuff, and I believe it was quite successful till now. What we also want to provide is a time-dependent presentation option and an interaction which allows people to hop between scenes and so. This is still not ready, but I told you it's an ongoing project. Well, some words about time. Time is important in teaching. First of all, I mean, from a fundamental point of view, because perception is time dependent. But it is also obvious if you consider time dependent media as video, audio, stuff like that, and if you want to connect these time dependent media to other, like illustrations or explanations, then you need to process time in the whole system. It is not quite that obvious, but also in static environments, time may be important. For instance, consider a language learning class where you do language comprehension or so, and the teaching goal is to give students to expose a certain text for a certain amount of time to students to test on this on the comprehension. More general, we believe that by being able to form a coherent time stream or coherent content stream, you have a much richer possibility of expressing a train of thought and complex contents. Yeah, the modeling in this whole area is sort of interesting but sort of complex. You have, if you consider time and if you consider media objects on your screen, you have a temporal and spatial arrangement you have to somehow deal with, which is, first of all, difficult to author. Consider, at least in the temporal aspect, you don't, and also in the structural way, you don't have a Wysiwyk paradigm. You can't Wysiwyk-like author this type of things. Also, if you want to process temporal stuff, you need some sorts of play scripts. Well, if you think a minute, you have two ways of handling this. One is just to form like a video type media stream on your server and push it to the people. And the other one is you individually process your objects, bring them up, maybe to your application, to your client, and deal with individual objects. We chose the latter one because we believe it's fascinating to give individual object handling and also to give the possibility of interactions there. But this needs a logic of an object model, which we formed in the following way. We chose as a central entity something we call media objects, which are sort of a container for data, for actual data, but also for additional media objects, so we can form a whole complex structure of media objects and data. The implementation of these media objects is done in an object-oriented fashion, and we are able to annotate freely those media objects by deriving them from classes. I'll show you a picture in a minute. They are all supposed to be reusable and self-consistent, so that in any place of your object hierarchy you are able to use them for demonstration purposes. One important thing we believe is that the object composition needs to be open for the semantic of the application. If a teacher comes along and wants to put some logic in the structuring, it must be open. It must not be related to technical stuff. Well, the document structuring is done by a flexible model to define object references and is able to be processed. Any reference can be processed either by event type interactions or, for instance, time processing. This is, for instance, let me say a word. In the time area, most of you know Smile as an HTML extension. This is one of the reasons we didn't experiment much with Smile, because to our understanding, Smile is just an extension of a tagging language like HTML, and is not able to handle objects in an object-oriented and complex fashion. Well, the media information repository, we called it. The name Mir was just free when the astronauts came down. It has the objective of giving a fundament for creating many types of teaching, teleteaching, multimedia teleteaching applications very easily, and it consists of three major parts. One is an object database, which first of all stores data, but which provides all that structuring I told you about, and which also is free in defining annotations in the sense that once you come up with an application or with the idea of an application, you can, without programming, form this database from a web front end. It also has an authoring environment, of course, which is the database editing, and it is able to provide application-specific interfaces. Well, and there's a general architecture which is open to and quite flexibly to a network client layer, and is open also for streaming subserver which can be plugged in. Yeah, the first overview I want to give you about the media object database. It consists of two major rows. On the left you see what we call just a data store. You have a flat data space where you can put in your data, and on the right you have a media object lattice. They are connected, structured, and you see in the middle two parts. The upper one is what I told you about the object-oriented scheme. All media objects are derived from object classes where you define the properties, and it's of course related to users because it's a multi-user system. Well, in the authoring environment, you see a user point of the system. On the left side, you see all data is organized in a virtual file system, just very transparent, very easy. But the important part is that your data editor, which is open here for an example, adapts to the type of object you just click on. Those objects are very different or very differing database objects, and once you try to edit one, you need a specific editor for each object. One should maybe say that this is the authoring environment is something like a toolbox which can be extended and can be also taken apart to handle all that stuff. Yeah, from the architecture point of view, well, it's a typically three-tiered architecture. You have a database I showed you. You have a middleware, and you're open to the clients. Defining the clients is left to the applications in this system. Interesting maybe that you have, beside the normal Corba IOP access, the ability to plug in subservice, as I mentioned earlier, and also you have a transparent web access to any object. Remember, they are all organized in a virtual file system, so you just can transform it into URLs without any problems. You access within the whole system. You access the middleware as like an application component server that brings along all properties like how to write, how to read, how to search, how to manipulate certain objects. Well, then let me come to the media objects in time. Specific application. This is only like a bit done like an animation from a real presentation. This is a system that runs in a web browser with a Java app in a Java applet, and this processes time-dependent data, including the web video. Well, it processes synchronized media streams, and it first of all brings the capability for an accurate temporal and spatial placement of any of those objects in the browser. And this is true for timeless objects, for just images, text, and also for streamed objects, as I mentioned, the video. It is also able to handle the composition of the objects. It resolves object structures. Well, what we did, remember I told you that in the general environment we took care that the structuring or the composition of objects is open to the application. In this case, we have an application, and we define the structuring in something we thought is intuitive and reasonable, and we did it in a way that being referenced by an object above means for you that you have a temporal and spatial inclusion relation. It is the object, your super object, dominates your space and time and the space and the time. This is also a consequence from this is that it's easy to have all these objects reusable because you don't have to care about time and space extensions, and it also makes it possible that all your objects include their own place scripts. So any object entity has its own place script, and they are run in the runtime system, which is we call a time-based flow generator. And it's one thing which is also important in web is it's suitable for very lightweight implementations on the client side. Yeah, the media objects here are still the universal containers and containing all data, all structural references, and the playlists. They do provide a local coordinate system in time and space, which is scalable. They are scalable and parameterizable for reuse, and the system also provides that they are self-consistent in the sense that they are recursion-free, and they are, by the temporal and spatial inclusion relation, they are self-consistent handably. Yeah, here's a visualization of this, just a tree structure in the sense because it's recursion-free, and on the bottom you have the different media objects, and each line denotes this temporal and spatial dependence. Some word about the flow generator. I told you any object in this object-oriented model has its own playlist, and you somehow have to deal with the fact that time is linear and the model not. What we do is we resolve all object place scripts, as you see in the bottom, individual instruction lists to form a big one, the one to be processed on the client. But this is all done on the client with the fact that the result that you can change it, that it's open to nonlinear interactions. This is one thing we are aiming at. So, a word about the web video. This is joint work with a group of Cisco et al. We are using Java implementation of a wavelet codec. Well, the advantage of the wavelet codecs is that they're very nice, scalable in many senses, and they don't have artifacts like we saw before. They don't show the typical artifacts like you have from JPEG or other type of things. They always produce real pictures. Being in the resolution type of thing, they might be not quite as sharp on the edges. Well, this specific codec, the PAC codec, has, first of all, it runs in a Java implementation in real time, which is, I believe, quite good. And it has some, there are two things about it. One is the bandwidth. You want to have a low bandwidth, and the other one is the computing power of your PC or of your machine to resolve or to calculate the images in real time. So I gave you two examples. If you have a QSIF format at 12 frames per second, we are still slightly below, in normal videos, we are still slightly below ISDN speed. And if you want to have a better picture, a TIFF format at a more moderate frame size of 5, it still performs in real time on a 500 megahertz or so Pentium machine in an applet, in a Java applet. Yeah, well, power quality, of course, is not sustainable with present Java and machine implementations. Oops. So, some word about the architecture and implementation of the media objects in time system. It relies on the three-tiered open multimedia architecture I showed you before. It uses the intelligence of the database by processing this structural links. It also brings with it an additional lightweight XML data storage, so you can extract all stuff to XML and carry it on your PC. So it provides the subserver instances, the streaming subserver instances also. I mean, the interface also on the client side. I showed the picture for earlier at the server side, but if you want to play it, you of course need a client, and if you want to integrate the client in like a presentation applet or so, you have to come up with either an interface or something. It uses the wavelet video, and it is pure Java. So, conclusions and outlook. I showed you something which is sort of which is sort of an application middleware, which consists of a universal database system, allowing for application-defined information structures, and also application-defined information at first, to free annotation to any object if you want so, which allows also for an active structuring and structuring that can be processed by the system. It is meant to designed to have reusable data, and it brings along in web authoring. The time synchronization was shown in the media objects in time example as one application of the mere environment, and which might be interesting in itself. The scalable video streams in the wavelet format are also included here. Work which is going on is the interaction model. It is modeled theoretically still, and the implementation will start, I believe, in the beginning of June. The interesting part here is that you want to, technically we are able to handle individual objects, but what you want, or what we want to come up with is something that is a very limited alphabet, very simple system, easy for the author, limited alphabet which is by the system, by the model, able to handle something like an unlimited number of interaction scenarios. So, since I still have time, I can show you two pictures of additional applications. One is totally different. It's called virtual design. It's an older one, being heavily used by our designers. This is a system just containing images, trying to relate images to each other by modeling the work process of design and visualizing it. You see a visualizing picture of these image structures here. Here you have the free structuring of the system used as just visualizing or implementing the work process of design. It's a totally different application, but capable with a system. And the second one, which is rather simple, but has the may show the real use of the system. It could be implemented in 10 days without very elaborate programming. It's what we call a knowledge marketplace. It defines knowledge structures and is able to keep or to hold media objects. And it is realized it's implemented by using XML and XSP, and accessing from the XSP side the middleware directly, so that it is more or less most of the work was related to giving it an outfit. So, I thank you very much.
Thank you very much for the presentation. Any questions? If there are no questions, then thank you for attending the session. And we have lunch now.